So here we are talking about a simple example of a two-layer, two hidden units neural network, and I'm trying to show the gradient descent step for some of the weights. So let's begin by drawing this network. So we start with two features, x1 and x2, and there's a bias term, so I'll add a 1 on the bottom. And we have one hidden layer, so we have our linear combinations called Z1, and this top on the top, the one is for the first hidden layer in case we have multiple, we only have one actually. So this is the second one, and the way to combine them is you get Z is just W1 multiplied by weight 1 to 1 first layer plus x2 multiplied by weight 2 to 1 hidden layer and our first bias term. Similarly, to get the other one, we just have a linear combination of these with different weights. So this is 1 to 2, number 1. This is 2 to 2, number 1. And this is just number 2 bias, first layer. Okay, and then these linear combinations connect by just activating it. So the activation function is G, and its activation is just A first layer first unit and A first layer second unit. So sorry, this should be 1 as well. And then in the next layer, there will be a Z and an A. So the linear combination variable, let's just call it Z2. There can be a 1. We don't really need this one. And it's just a linear combination. Of course, we missed a 1, so we need to add a 1. So this is called W2. It's kind of 1 to 1, so let's just write down 1. And this is the second layer weight, number 2 to the only 1. And this is the second layer bias, there's only one bias. And these ones are linked by the activation function G. And what's this? This is the second layer activation. There's only one, so I'll not do that. So, and this A can be converted by checking whether it's larger than say 0.5 to get our prediction y hat, but we don't need that. What we need is the cost function. So the cost function is basically the sum. Let's ignore the sum. Let's only have half of the actual minus, it's actually reversed, but it's okay, squared. And since we didn't have I anywhere, so we don't need that. So suppose we only have one example, and that example is x1, x2, and 1. Okay, so now the problem is how to do gradient descent. We need the gradient. So let's first try to calculate something that's easy. The derivative with respect to, say, this one here, W1, 2. So if you follow the arrows backwards, then you can actually see the chain rule. So we just differentiate with respect to the first one, so this one, and then we just multiply by going backwards, this one with respect to Z, and then going backwards again, we just got that. So Z2 to W1, 2. And let's do this one by one. So this is the derivatives between z and w's are very easy. It's just the x. It's just the linear combination. So this one is just a1, 1. And what about this? This is a to z. So the derivative is going this direction. It's just the derivative of g. So remember, we are doing logistic stuff. So the derivative of g is just activation multiplied by 1 minus the activation. So this is a2 times 1 minus a2. So, and going back, which is this direction, this is just square. Square cancels out with this 2. So we're only left with, sorry, this should be reversed, a2 minus y. So if it's not reversed, when you differentiate, you have a minus sign in front, so it gets to that as well, so it doesn't really matter. So now we have this, and we can calculate this and the bias term the same way. So I'll not repeat. However, something that's different is how to do this. So it seems to be a longer chain. Let's try to get that. So we want to differentiate C with respect to this W111. What is this? Again, follow this thing backwards. That's why the algorithm is called back propagation. It's just following the arrows backwards, backwards, backwards until it hits that. So the first step, let's jump some step so we can directly do this because we know this from our previous calculation. And we have this with respect to what? This with respect to A11, and then this A11 has a derivative with respect to Z, and finally this Z has a derivative with respect to our target. This is actually very quick because again, this one is linear. All the Z to W's are just whatever this input is, so X1. And what about this? This is A to Z. A to Z is always G related, so it's just A times 1 minus A dot. And the only new one is Z to A. Here we did Z to W, and here we're doing Z to A. So this thing becomes W. So this is W1, 2. And the last one, I'm not going to do it. This is just copying the first part. Let's highlight this, put it there. So if we multiply all of these things, then we get our derivative. The same thing happens with all of these, like there are 6 of those, but the idea is exactly the same.